glad to be here again at Buzzwords and happy to talk to you today. Thanks for coming. So I'll begin with, as you can see, the title slide. I'll talk about SEI. So that's Superlink's inference engine, which is an open source solution that basically helps you self-host models, but also ships the cluster and the infrastructure around the models themselves. And in that whole process, I will talk about today, because I have 40 minutes, so that's a lot of time. I will talk about different details around this, what you can use SEI for, and how you can actually use it to build inference around agents, and how you can think about small model inference in the shape of inference for agents. I will talk about how in the past we used to build search, maybe how the production pipelines look like now, but how they look like in the past, and how this solution offers you kind of a few things here and there that can help you modernize and make things more flexible in your full end-to-end search workflow. And I will go into details into how it works now and what kind of design decisions we've made when building SEI that will be interesting for you, especially if you're hosting search, working with models, trying things out, thinking of like, oh, I have this managed service, I want to ship it out and try self-hosted versions. And we have a GitHub repo, fully open source. You can check it out. I have that as a footer on all my slides because I really want your opinion. People at Buzzwords have been at the forefront of search for many years, so I'd be very happy for you to try this out and test things out. And we also offer free compute for people that build things that are interesting. So keep that in mind and feel free to contact me on LinkedIn and you'll find me around SEI's content. So I will begin with inference for agents. The idea here is that small model inference can be framed as something that agents can use. And why this is the case? Because we all know about context rot, and there was this study by Chroma done a few years ago, where we are all aware of the model's inability to kind of process things in the middle or forget context and so on. And what has been proven to work is using small models to kind of pre-process and prune this context of the data and the window, so that then once it hits the bigger models, you have a more, let's say, pruned and more relevant context that actually you spend your tokens on instead of just doing everything from the get-go. And this can be framed into these three key pillars. So it can be framed as like a job of retrieval or trying to find something. So this is based around embeddings and trying to retrieve the right information, get the right embeddings. Then there is the step of prioritizing and understanding that, okay, once I've retrieved the relevant stuff, how I can re-rank them. So that's re-ranking models. And then there is the part of structuring, right? So if we look at this workflow as, okay, I want to use small models and use this agentic inference in order to pre-process my context, I will need to eventually figure out some structure of like maybe entity extraction or like structure generation. And all these three tasks are what you need to do if you wanted to do agentic inference. And you would need to use small models and multiple small models. So this is not just one model, but a series of more models. And this is very similar to how a search pipeline would work in the modern day today. For example, even if you use stuff like ColBERT, you would have one model that does the late interaction and kind of getting the context in there, then having like sparse model to match some more literal terms or like IDs and so on, and then a reranker in the end to figure out your final ranking. So this agentic inference is very similar model-wise in terms of what models you need, what models you need to support, what kind of infrastructure you would need to support to a standard search pipeline. And this is the case even in production. So we have this example of like a taxonomy classification workflow. And these are some highlights of things you can do. So you can use text extraction and, for example, stuff around structure generation, metadata to index switches, or if you want to do vision stuff, because all of these e-commerce things have images and so on. So there is the Qwen 3 vision model that you can use, and there is also the query parsing aspect. So again, even in this specific production scenario, which you can find in our docs page, you have this situation where, okay, I need a workflow of multiple models, whether I'm building agentic search or whether I'm building a more standard search workflow, I need to support multiple models and I need the infrastructure for it. And in this way, we have built SAI to kind of enable you to actually do these tasks that all these models, let's say, do in their own little sub area of work by thinking of them as like tools for the agents. So for example, you can have a parse document bundle that includes multiple models that do OCR, structure generation, extraction, and then basically with SAI, you can get an agent that calls these specific tools that basically package these models and do inference and deployment in the way that I explained just before. And I think that's a key step here, that you can look at this process of agentic search and agentic tool calling in, let's say, multiple ways. You can zoom out or zoom in. And we like to think about this as like these little boxes where you have maybe multiple models that are bounded to a specific task, and then you can chain them together with what we're building and kind of build your whole agentic search pipeline. And this is a good kind of, you'll have the slides as well. This is a good reference to have. So that was the presentation of how we look maybe at the future and how we look at the current modern search deployments. But now I want to go a bit back and talk about how we used to do these things and what kind of prompted us to actually build SAI and actually think about what I was describing before. And then after I explain how we used to do things, I will dive deeper into the tech. So what I was speaking up until now was more the task level, let's say, explanation. Now we slowly get deeper into some details. So we used to do this. Multiple GPUs, if you need multiple models, you need separate deployments, separate hardware, and you put different models in each GPU. So you can see, for example, a reranker that can be served by HuggingFace's text embedding inference, another extraction model on another GPU, another vision model, then the query processing in another. If you want a late interaction model, that requires a separate runtime, separate GPU. So then you end up in a situation where you have, in order to build one search pipeline, you need to maintain 6 GPUs, 6 separate deployments, different runtimes. And if you do this at scale, things can get quite messy. And that was the first maybe red flag in our work in the past. And this is a problem because you have the problem of scale. You need to maintain multiple deployments. And also there is the problem of GPU allocation. So if you want to switch between models, put maybe one GPU down so that it's not always on and kind of staying idle. It's a complex problem to have, and it spreads out and maybe accumulates as a problem for your whole engineering team when you do this at scale in production. And this kind of directed us to go in the direction of multiple models to one GPU, like you can see here. So basically, we have a policy of least recently used eviction that we do now, where you can substitute multiple models and get them in one GPU. And because these are smaller models that are like rerankers, embedders, late interaction models, there is enough memory to do this switch around and kind of replace models and use one GPU. And these are the things that we were hand building in the past. So we were chaining different tools, but nothing was hitting quite right in terms of what we wanted to do. So we had a lot of out-of-memory errors. We had problems understanding the batch sizing, a lot of code around batching as well. We were also locked in, so we used to work with modal only, and we couldn't kind of self-deploy this to our own VPC. And that was a problem. So the main one, the first one, was that out of memory was just a thing that we would try again and again. So there wasn't a thing that's set up. We would just say, oh, if it's out of memory, then try to lower the batch size, which doesn't sound too kind of engineering heavy, let's say. So we wanted a better, smoother solution. And now we're doing stuff that are more advanced in the sense that we have the batches are cost bounded before we have this setup done before all of this out of memory errors happen. We have the eviction of models, so all of this is handled a lot smoother now. Also, batch size is not something that we just like now manually tune by hand and figure out, but actually there is a max batch token because we do token-based batching. So I'll go deeper into that a bit later. So why it's not just request batching, because different requests can be of different token size, and that means different usage of your resources. And we have this controlled batching strategy that uses a proportional and an integral controller, similar to how you would maybe work with a more advanced thermostat in, let's say, the more everyday world. And another problem we had was that this only ran on model. So we used model and infinity in the past. So we weren't able to sort this out of memory errors. We weren't able to deploy things on one GPU. We weren't able to control this batch sizes and so on. But also we could only run things on model. And that was a problem because we wanted to maybe change the container number, change the location, change how the requests were routed. If we wanted true self-hosting, that also wasn't possible. So now what we do is we basically ship the whole cluster where you have a Helm chart, so you can build your Kubernetes clusters. We have also Terraform, so you can define basically, we give you the code in Terraform so you can define your infrastructure and build things on your own cloud. And now I'll go into how it works now and certain design decisions that we've made in this process. So it wasn't just like, okay, we're trying to figure out these things and that's it, but we wanted to make a more universal solution that people can try out directly, build their agents, build their pipelines centered around inference. And the way that our API works is kind of based on 3 primitives right now around scoring, encoding, and extracting. So this is like encode if you use an embedding model, scoring if you use a reranking model, and extraction if you use something like named entity recognition. But we're also supporting token generation models and OCR models. So the catalog of models expands day by day. So we support like more than 100 models right now that you can try out and work with. And this is maybe a rough overview of how the architecture of Psi looks. So we have also like a gateway that we wrote in Rust now. So we're also optimizing kind of the infrastructure code as well. And we have, as you can see, multiple workers or multiple worker pools. So for example, if you have some smaller models and care about cost a lot, you can use a worker pool that has L4 spot instances, so you don't need much performance, too much memory, so you can use that. But if you need something more powerful, you can use a worker pool with A100s, for example, or even something bigger. And we have a batching technique that I will get into a bit more detail in the next slides, but this is the cool overview that you can have kind of the gateway routing mechanism written in Rust the batching and the infrastructure around the workers. And the design decisions around the batching and model choice. So these are the two things. Basically, you want to have, as I said, this OCR, embedding models, reranking models, Quen, different providers, different open source models. So you want to be able to use this model, so support them. And we have this set up as like a config where you can just tune the parameters and decide which models you want to use. So here are a few examples with Quen and the paddle OCR models. And this is a much more smoother way to interact with models than just like working with some API. And when supporting models, one big problem is that there is no universal runtime for how models work. So, for example, one set of model families, they implement attention in one way. Another implement positional encodings in another way. One uses grouped query attention, another doesn't. So these are things that you have to adapt to, and you cannot just have a universal runtime for any model, no matter what task. So this also requires a lot of work, and we have set things up in a way that there are different model bundles. We divide them by categories, by way of implementation. We rewrite the forward passes for certain models in order for you to have the best version of the model that you can use and not have, for example, if you go to VLLM and you select one model, you can see that there are at least 10 issues for each model for it not working properly, and there are some errors. So we wanted to make sure that, okay, if you use a model, you can actually tune the things that you want, but you also get the proper runtime that does well for your task. And once we have the model support figured out, now it's more about the infrastructure and the performance, and how do we actually take these models and get them in your production environment, VPC, or you test them out with our test cluster, for which if you build a project, we offer free credits, so keep that in mind as well. And this is maybe kind of a simple GPU profiling drawing where you can see that the GPU compute is the main thing that occupies the GPU, and if you can limit this or lower this forward pass request, you've saved a lot of GPU time. And the GPU time per item gets lower as you have a bigger batch. So the idea is that if you can utilize your GPU more, the cost per item gets lower, and that's good. And it means you utilize your GPUs better. So we have thought about this, and the idea was to kind of have this as a thought before building this. So how can we figure out a way that you can actually utilize your GPUs properly in this complex environment with multiple model runtimes, with multiple tasks, with multiple batching techniques? So that's how we approached it. And there are different ideas here around whether you should wait for a batch or just like fire right away. And here I talked a bit about that proportional and integral controller that we've built that tries to kind of balance this. The idea here is that basically I will showcase this in this slide here. So how previously or how maybe the industry works right now is something as shown in this animation. So on the left, that's how, for example, TEI, or text embedding inference from HuggingFace, would work. So there are separate queues per each worker. And we, in our tests and kind of engineering effort, we understood that by making the small adjustment where this queue is moved not to each worker, but as one big shared queue in the beginning. So you can see kind of on the right how the requests pass through the gateway and go into one big shared queue. And then each worker pulls from that queue. You end up with higher GPU utilization because you're able to kind of max out the batches based on the demand and based on the hardware capacity in a much more efficient way than how it is done currently by most model inference provider. providers. And only this small one change gave us immense differences in kind of performance results and GPU utilization. So this is a key thing and a design decision that we've set up. And you also get this open source, so this is not behind a paywall or anything like that. And what we also do is that we batch by tokens, so not request count, because in AI, not all requests are not the same. Some requests have a higher number of tokens, some can have a smaller number of tokens. So you need to evaluate how complex the requests are by their token sizes and not just the count. So this is another element that kind of makes this GPU utilization much better than what maybe was the standard in the past. And as I mentioned before, we also have the third key infrastructure decision where you can hot swap models into the same GPU. So you don't have to have multiple GPU deployments where you kind of keep the whole GPU busy for one model and don't utilize the full GPU, but you can have, as you can see kind of on the right side, you can have multiple models on one GPU and they're hot swapped by the least recently used eviction. And this gives you a much more utilized GPU with a lot of kind of options for you to test things out and not having to maintain this many, let's say, GPUs and hardware and kind of have the observability and scaling. It's much simpler to do everything on one GPU. And how this would look like maybe in a more business case scenario is that you would have self-hosted inference and it would keep the data inside your platform. So as I said, in the past, we use model, or if you use a managed provider, you don't have that guarantee in a way, and you can kind of self-host everything. Usually, if you don't do that, you would have to kind of maintain some managed model inference like Together AI or Base 10, and then have the LLM API as well, like either from Bedrock or like the direct OpenAI API. And instead of that, you can have everything in your platform. And we also wrap some of this runtime. So for example, we use SGLang and we wrap the infrastructure around it. So we have this optimized very well around each of the models. So we put great care in how we pick the models as well. So we have, for example, the way we support models is by evaluating their benchmark scores on specific tasks. So we do not just pick models randomly or by hype or popularity, but we have internal evals that we run that are kind of narrowed down on specific tasks. And that's how we rank the models and see how they perform. So not just like average scores that are published somewhere, but it's more around the whole performance of the model in the specific task. Because as I mentioned earlier, right, we have this agentic tool calling step where if you want to do stuff around OCR, you only care about that specific performance of the model in maybe your subdomain of finance or medical images. You want to know, okay, which model is best in this subset of tasks, not in the general realm of OCR models. So we also have this detail in mind when we try to select models. And this is kind of an info chart that you can have a look at, where we compare and how we compare between certain other runtimes and solutions that might be similar. But the main idea is that usually there is the model inference providers that do not help you or ship the cluster and the infrastructure around it. So what we do is we give you both. So you have the model choice and model inference support. So you have coverage of all sorts of models. So whether you're doing OCR with vision, reranking, LLM, normal LLM token generation, you have that option. So you have those models optimized and you have the model choice. But also you have the cloud setup that helps you actually run Kubernetes clusters, provision your own hardware, or set up your infrastructure in a way that you can best utilize these models at a production scale. And also there is this, for example, compared to TEI, so TEI has to run each model on a separate GPU. So there is no multi-model per GPU deployment option. And this is the case with a lot of the other competitors. For example, with VLLM, as I mentioned before, if you go to the issues tab, there are a lot of errors and kind of things failing for each model in production. So we wanted to pick the lessons from there as well and understand that, okay, we want to have the models run well, but also help you have the infrastructure to actually use those models, not just have this per model. And the reason, and maybe one objection that we often get, is that, well, I want to use a managed open API service. I don't want to use open source models. However, we've seen that more and more open source is catching up. So now it seems like there is like a gap of 2 months where the frontier models are ahead of the open source models. But this gap is narrowing down and token costs are going up. So there is this kind of use case for open models where open source is doing better and better and even catching up to managed solutions. So if you can lower the cost a bit, have your data be in your own cloud, have this, let's say, sovereign AI on your GPU, there is this stronger case to be made that kind of advocates for open models. And as time goes, I think this argument gets stronger and stronger. And what we've done so far, roughly, we've tested this out with a lot of our partners. So we have native integrations with Chroma, Quadrant, VV8, LensDB. And here you can see a few quotes of like people in those companies, quite, let's say, key people in those companies trying things out and testing us out and working with these integrations. And what you can see at the bottom there is this examples that we have, like use cases that were built based on our lessons from production and what kind of the community has used Sai for. And there's work around OCR models. There is stuff around, we have one example of like a compliance RAG pipeline that also uses LoRa fine-tuning. So basically we allow people to host LoRa fine-tunes of the model. So the fact that we support this many models with different runtime types means that if you do some fine-tune of a model for your proprietary data, you can actually still use Sai and use that model for your own use case and in your own cloud. And it's as seamless as using the generic, let's say, model. And feel free to look at these examples and integrations. And again, if you build something similar, we're offering to sponsor free compute so that you can test things out and have a go at our repo, because we love your feedback. And this is kind of a bit of a summary of what we've learned. The first thing is that, as I said, the production stack involves multiple small models. So it's not one model. It's something that you can run maybe as a service if you're building agent to have like this, okay, I want this document parser unit that involves multiple models, but you encounter the problem of like, I need multiple models to run this task properly. And in order to build the infrastructure for these multiple models, you need to do a lot of work. So that's what we're trying to do, and where we're simplifying the process, where you can just basically plug and play and use these multiple models and hot swap things and test things out. And it's important how you use your GPUs, how your GPUs are utilized, what you can do in terms of batching and queuing techniques, how you set things up there is important. So we help you with that as well. And open source models, smaller models are catching up. So you have more and more powerful models that can be on par with managed services in the stuff that you built, especially around smaller specific tasks. And you can also keep stuff in your own cloud. So no need to kind of share your data or be scared that you have any privacy concerns. You can do this in your own cloud, and we fully support that. And we're happy to kind of help, even if you have some questions around that. We're open to discuss things on our repo or messaging me directly. And this is the repo, so you can have a look at the QR code and give us a star. That means a lot to us. But yeah, basically we offer this free compute for examples. We're very serious about this, and especially at a conference like this, please do get in touch and talk to us about this, because what the community wants is something that we value highly, because this is how we've learned about SCI and how we ended up building this thing from our interaction with a lot of engineers, a lot of production deployments being stuck around inference, and that was the biggest problem in our search pipeline. So happy to hear your comments, and also happy to hear your questions now, as yeah, I'll leave this slide on, and happy to talk to you if you have any questions now or after as well. Thank you.
Questions? I'm sure there will be many.
Hi, Filip.
Hi.
Thanks for this very inspiring talk. I have a kind of complementary question. What if you have like around 10 models running on more than 100 GPUs with VLLM, and we have no manpower to migrate to SIE? So what is your suggestion? What is the optimal way to test it?
So you have no power to migrate, to say?
No manpower.
Well, we can, in specific cases, I think if we can discuss this, like we're happy to help you set things up. And I think given what your use case might be, I think there is an option for us to look into it and help you out kind of to set things up. But definitely, yeah, we're interested, because this kind of the work with, especially with the embeddings and like batching, you save a lot if you have huge batches. So yeah, happy to look into that and discuss, because we have also people in the community that have built stuff. We also have our own great infrastructure team. So yeah, we can discuss.
Yeah, thank you.
Okay. More questions?
Hello. My question is like, if I get it right from the presentation, this is great for throughput limited applications. But have you also tested like latency critical applications, or is it also improving if you improve the throughput of the system?
Yeah, so I think with the way it works, I think I have it somewhere. Like you can set up different targets based on what you want. So you can set up like a target latency, and then we kind of set up the batching based on the controller for what your latency target is. So there's definitely like you can pick however you want to set these constraints up. And obviously, yeah, if you have the kind of the right hardware, you can set up the logic just by configuring the latency targets and the batches and the wait times, and then our queuing mechanism seems to work quite well. Obviously, right, it depends on the model choice and so on, and depending what these numbers are. But definitely we've seen this work even with like different sorts of latency parameters, batch sizes, different models, and yeah.
Have you got anything built in for if you want to try multiple different models in parallel? So if I was wondering about using 2 different OCR engines where I can send the same data, then the pipeline splits it, and then at the end I can say, it looks like that model was better for this query, so I'll use that answer.
Yeah, like you mean kind of like a model routing and then some evals tied into it.
Yeah, so we sort of split it, we run it multiple times, and we say, it looks like at the moment that one's better, so then long term we'll stick with that one.
Yeah, I mean, so we don't have that set up as like some specific use case you can plug and play right away, but definitely like you can use different models. Even all of them can be OCRs, and then if you have some eval somewhere after, that's possible. But again, the way we pick models is like eval driven. So for example, the model support and model choice in itself is in this direction. So for example, if you want to run some specific evals that are your own locally before deploying things, that's also possible. And I think we can do that as well, because it's quite, let's say, our ethos as well in how we decided to pick models and have the model choice. Yeah. And that's also team member, our CEO, Daniel.
Hello. So the model name is a part of the request. So basically, if you have an eval, you want to try a bunch of different models, you just say, I want to process this input with this model, same input with the different model. And then basically they get like lazy loaded into the workers. And we are releasing a feature that you can also pin the models. So you can pin capacity in worker pools, but you cannot pin models right now. But so you have to pre-warm basically. And some of these models can take like minutes to load. But we also have a way to like pre-download the weights to cloud storage, and then you can run kind of air-gapped, and also the loading is faster. But yeah, like certainly the eval workloads are one of the workloads we target.
A little bit off topic, but what are your opinion the hottest trends in large language models right at the moment?
The opinion on, sorry?
What are the hottest current trends in large language models? What are we to be excited about in the next year, for example?
Good question. I think the whole space is moving very quickly. I think there is value in understanding smaller models and task-specific models, because now with all the IPOs and movement in the market, token prices will be going up. So understanding where this cost can be cut down, or like task-specific models can be used, I think that's an interesting way to look at things, where you can combine the big models with something that's task-specific. So I think this workflows will be shaping up and showing up more often, let's say in the next few months. And we've seen the rise of like agentic harnesses as well, which are kind of along these lines, where you try to solve this little task-specific problems, and then have the bigger model be like an orchestrator that picks its tools. So each tool can be a smaller model or a series of models. So I think that kind of harnessing that uses smaller models is something that will be showing up more and more.
One question from me. Have you heard about the Tokenomics Foundation? Started a few days ago about calculating the economy of token usage and producing some standards. Are you kind of part of it or looking at that?
Which foundation? I think
Tokenomics. It's just part of the Linux Software Foundation. They announced it a few days ago.
Okay.
Actually.
Well, no, I haven't been caught up with this from a few days ago. But
speaking of like things getting
no, that sounds
very fast.
Yeah, it sounds interesting, and I think definitely we need to at least have the insight of how our tokens are spent, and that
exactly
helps us. What we can measure, we can track and improve.
Exactly.
Well, thanks for the thorough talk and for the explanation of the whole journey. It's been super interesting. You were talking about evaluation, and I was wondering, what do you use for evaluating? If it's generalistic benchmarks or something you build yourself, and how does it evolve depending on the clients you have and so on?
Yeah. So yeah, initially we started, so we have some internal evals that are like task-specific or client-specific, and that we tune to specific tasks. But initially we started with MTAB. So with MTAB, there is this like model evals, but they're like an average of the model performing on different tasks and different types of data. What we did was we analyzed the per task performance of each model. So in that way, we kind of re-ranked the model's performance based on the specific task. And sometimes it's like the model underperforms. So the top model on average underperforms in the specific task that's like very niche and that you might need like receipt processing from images. That might be there might be a model that's kind of on average the best, but in that specific task has a lower performance. So we started there, and that was kind of our evals journey where, okay, let's see what's out there, but narrow it down and then combine it with some of our internal work.
Okay, yeah. I also wanted to thank you for your presentation, and I was wondering mainly about like often deploying this in production also implies having observability and metrics and all that, and many of the runtimes you are using, I'm sure, export metrics in a different way. Do you have a normalization layer for exporting those metrics in a consistent manner for observability? How do you handle that?
So as in, you mean for like for the model performance or like the infrastructure?
Like both, like Prometheus metrics, where you might see like the throughput or the usage, or
Yeah. So I don't know if we have a normalization layer for that. Maybe, maybe we can have the crowd answer that question. There.
Yes. So we conform to OpenTelemetry, and we actually ship Grafana dashboard also with a bunch of different screens, or you can hook it up to your like standard cloud monitoring. So you have like the queue depth and all the auto-scaling signals and all that.
Yeah, we have CAD auto-scaling, yes.
Yeah, thank you very much. That will, unfortunately, we don't have much more time. Thank you. That was really great presentation. Big clap, big applause, please.
Thank you.